Universal law of gravitation. According to this law, the force of attraction between two particles or two bodies is directly proportional to the product of their masses and inversely proportional to the square of distance between them. Suppose we consider two bodies A and B having masses m1 and m2 respectively. Let the distance between these two bodies is r, and according to law of gravitation, the force of attraction F, or force of gravitation between the bodies, this is directly proportional to the product of masses, that is F proportional to m1 m2, and is inversely proportional to the square of distance between them, that is F proportional to 1 by r square. Combining these two equations, we get F proportional to m1 m2 by r square, or we can write this as F equal to g into m1 m2 by r square. This g is called universal gravitational constant. This is the mathematical form of Newton's law of gravitation. In this formula, the magnitude of force, this varies inversely with the square of the distance between the two particles. Hence it is called inverse square law. According to this, force of gravitation is directly proportional to 1 by r square, where r is the distance between these two particles. The value of g is 6.67 into 10 power minus 11 Newton meter square per kg square. This is in SI, and g is called universal gravitational constant. We can define g as the force between two objects having unit mass separated by unit distance. In this formula, if we consider m1 equal to m2 equal to 1 kg, r equal to 1 meter, then we get g equal to F. That is, the value of universal gravitational constant is nothing but the force between two unit masses separated by unit distance. Let us consider the force between two masses m1 and m2, which are separated by a distance r, is F. That is F equal to g m1 m2 by r square. If the distance is doubled, then what happens? Yes, the force is directly proportional to 1 by r square. If the distance is doubled, F prime proportional to 1 by 2r square, then new force becomes 1 by 4th of initial force. That is, if the distance between two particles is doubled, the gravitational force becomes 1/4. If the distance between the particles is halved, then what happens to gravitational force? F proportional to 1 by r square. When the distance is halved, that is, it becomes r by 2, then F prime is directly proportional to 1 by r by 2 whole square. Now F prime by F, this is nothing but 4r square by r square, or 4. That is, when the distance between the two particles is halved, the gravitational force becomes 4 times. F equal to g into m1 m2 by r square. This g is called universal gravitational constant. The importance of universal law of gravitation is the gravitational force is one of the fundamental forces in nature, and this is responsible for solar system, that is motion of planets around the sun, holding the atmosphere near the surface of the earth, the flow of water in rivers, for rainfall and snowfall, motion of the moon around the earth. Because of gravitation only, the tides will occur, and it helps us in prediction about solar and lunar eclipses. The universe exists because of this gravitation. Without gravitation, there is no universe. The characteristics of gravitational force. The gravitational force between two bodies or objects does not need any contact between them. That means it is an action at a distance. Gravitational force between two bodies varies inversely proportional to the square of the distance between them. Hence, gravitational force is an inverse square law. And gravitational force between two bodies or objects is an action-reaction pair. Suppose we consider two masses A and B. On this mass, a gravitational force is acting due to mass B. Similarly, on B, a gravitational force is acting due to A. And these two are equal and opposite in direction. That is, we can write F1 equal to minus F2, where F1 is force on B due to A and F2 is force on A due to B. And using this formula F equal to G into M1 M2 by R square, we can find the gravitational force acting between any two masses. And one more characteristics of gravitational forces, it is independent of medium present between the masses. That means, suppose we consider two masses m1 and m2 in air. Let us consider F as the gravitational force acting between them. If the same masses are taken in water, then also the gravitational force between them is same. It is independent of nature of material that present between the masses. Now let us try to understand what is the acceleration due to gravity. According to Newton's third law, to every action, there is always an equal and opposite reaction. That means, if an object A exerts some force on another object B, then the object B exerts equal and opposite force on object A at the same instant. This law applies to the force of gravitation also. Suppose we consider an object of mass m, small m, is at some distance from the earth as are seen in the figure. And between these two masses, the gravitational force is acting. The force on this object due to earth is equal to the force on the earth due to this object. And these two forces are equal and opposite in magnitude. And because of these forces, the body will get acceleration. We know that force is equal to mass into acceleration. And because of this force, the mass gets the acceleration. At the same time, earth also get acceleration. But the mass of the earth is very huge. In this equation F equal to ma, m is very large. There is no change in F. Then what about A? The acceleration of earth is very small, but the acceleration of this body is more, and it moves with some acceleration towards the earth. The acceleration gained by this body due to attractive force of the earth or due to gravitational force, it is called acceleration due to gravity, and the value of acceleration due to gravity is 9.8 meter per second square. This is acceleration due to gravity. Now let us try to derive an expression for acceleration due to gravity of the earth. Consider an object of mass m on the surface of the earth. Let capital M is the mass of the earth, capital R is the radius of the earth. In this case, the object is at a distance r from the center of the earth. The gravitational force between the mass and object is F equal to G into small m capital M by R square, where small m is mass of the object, capital M is mass of the earth. R is the distance between the center of these two objects. If G is acceleration due to gravity, the weight of the object is given by F equal to mg. This is acting vertically down. This is the gravitational force due to earth on the object. And this is nothing but the gravitational force acting between two objects. Therefore, we can write m into g is equal to gmm by r square, or small g equal to g into capital M divided by capital R, where capital M is the mass of the earth, capital R is the radius of the earth, and this is the acceleration due to gravity on surface of the earth. Now using this equation, we can find the acceleration due to gravity on the surface of any planet. Now the question is, the value of G is same at all places? The value of G varies from place to place on Earth, and also it varies from planet to planet. The value of G depends on the mass of the planet and radius of the planet. If you go for Moon, since the mass and radius of the Moon are less compared to Earth, automatically the value of G, that is acceleration due to gravity, on Moon is less compared to Earth. If you go for Jupiter, mass, radius of Jupiter are more compared to Earth. Therefore, the acceleration due to gravity on Jupiter is more compared to Earth. Then what about Sun? Sun is very large compared to Earth. Therefore, the value of acceleration due to gravity on Sun is very huge compared to Earth. Within a planet also, the value of G varies with the shape of the planet. We know that the acceleration due to gravity g is given by gm by r square, and the expression for g calculated by considering the Earth as a spherical body. But Earth is not a perfect sphere. It is in elliptical shape as we are seeing in the figure. Therefore, the radius of the Earth is not constant throughout. The value of g is different at different positions. The equatorial radius of the Earth is high compared to polar radius. Therefore, at equator, the value of g is g equal to gm by re square, and at poles, the value of g is gp equal to gm by rp square. Therefore, gp by ge, that is acceleration due to gravity at poles to acceleration due to gravity at equator, this is equal to re by rp whole square. Already we know that Re greater than Rp. Therefore, Gp greater than Ge. Therefore, the value of G is more at poles compared to equator. As we move from equator to poles, the value of G increases. It is maximum at poles, minimum at equator. Suppose we weigh 1 kg of sugar at equator as well as at poles. Where we get more amount of sugar, at equator or at poles? Just you think about this question. Now we discuss about a variation of value of g with height. We know that the acceleration due to gravity on the surface of the earth is given by g equal to gm by r square, where r is the radius of the earth, m is mass, and g is universal gravitational constant. Now what is the value of g at height h from the surface? This is nothing but gm by r plus h whole square. Now from these two equations we can write gh by g, this is equal to gm by r plus h whole square into r square by gm, that is gh by g, this is equal to r by r plus h whole square. R plus h is greater compared to r. gh by g is less than 1. gh by g equal to r by r plus h whole square. This is the relation between the value of acceleration due to gravity at height h and on Earth's surface. If the value of h is very small, now this can be written as gh. This is equal to g into 1 by 1 plus h by r whole square, and using mathematical relations, we can write this as gh is equal to g into 1 minus 2h by r. If the value of h is very small, if the value of h is very less compared to the radius of the earth, then we can apply this formula. And now we discuss about variation in the value of g with the depth below the surface of the earth. On the surface of the earth, the value of acceleration due to gravity, this is given by g equal to gm by r square. If we consider earth is a sphere, writing mass is equal to volume into density, this can be written as g into 4 by 3 pi r cube small d divided by r square. Here r is the radius of the earth, d is the density of the earth. Now this is equal to g into 4 by 3 pi r d. Now the acceleration due to gravity at some depth h, this is given by g into 4 by 3 pi r minus h into d. At g equal to gm by r square, capital M is mass of the earth, capital R is the radius. When we go into depth h, at this position, the value of g is due to the sphere within this radius r minus d. Therefore, at this position, the mass is different. Hence here we are writing mass in terms of density. Now from these two equations we can write gd divided by g, this is equal to g into 4 by 3 pi r minus h into d divided by g into 4 by 3 pi rd, or this is equal to r minus h by r, or the acceleration due to gravity at the depth h is gd equal to g into 1 minus h by r. As r minus h by r less than 1, we can say the value of gd is less compared to g. That means as we are moving into the earth, the value of g decreases. Similarly, as we move up from the earth, then also the value of g decreases. At the center of the earth, h is equal to r and acceleration due to gravity becomes 0. This is about the variation of acceleration due to gravity with depth. Motion of planets, moon, sun, etc. puzzled many scientists. It was Ptolemy in the 2nd century AD who put forward a theory known as geocentric theory. According to this theory, Earth is the center of the universe. All other planets, including Sun, revolves around the Earth. This theory is also known as Ptolemaic theory. And geocentric theory was accepted until Copernicus. Copernicus, a Polish monk, proposed a theory known as heliocentric theory. According to heliocentric theory, Earth along with other planets revolves around the Sun in a circular orbit. And this theory was accepted for many years. And then Kepler, an assistant of Tycho Brahe, who analyzed the observations of Brahe and supported the heliocentric theory and put forward as a result in the form of laws called as Kepler's laws. At present, all physicists follow these laws related to planetary motion. The first law of Kepler, this law is also known as law of orbits. First law of Kepler states that all planets revolve around the Sun in an elliptical orbit of different radii, with the Sun at one of their foci points. Already you know that what is an ellipse, and you know ellipse is having two axes. This longer axis is called major axis and the shorter axis is called minor axis. And these 2 points, F1 and F2, these are called two foci. According to Kepler's first law, a planet revolves around the Sun in this orbit so that Sun is one of its foci. When planet is moving around the Sun, at some point it is nearer, at some point it is far away. But throughout this orbit, the angular momentum is constant. And using this principle, you can expect what are the velocities at different points. Yes, when it is nearer, the velocity is somewhat more compared to when it is away from the Sun. Consider the system of Sun and planet, due to which force the planet is moving around the Sun. Yes, due to gravitational force between planet and Sun. It is a mutual interaction between Sun and planet. Is there any external forces acting on the system? No. Is there any external torque is acting on the system? No. Since there is no external torque is acting on the system, the angular momentum of the system remains constant. Already we know that if external torque is 0, the angular momentum remains constant. In this case, the angular momentum is constant. And this distance, when the planet is nearer, it is called perihelion, and the distance when it is away from the Sun is called aphelion. Periheli and apheli. In general, the distance between Sun and the planet is taken as the average of these two. Now we go for second law of Kepler. According to this law, an imaginary line drawn from Sun to planet, which is also called radius vector, sweeps out equal areas and equal intervals of time. Suppose you consider a planet is moving around the Sun, as I was saying in the figure. Let A and B are two positions of the planet for a period of 1 month. C and D are also two positions related to time interval 1 month. The line joining Sun and planet sweeps some area at this position. If you compare these two areas are equal. This is Kepler's second law. Suppose if I consider 12 equal intervals of year, that is 12 months, the area swept during these 12 months are equal. That is, the Kepler's second law is imaginary line drawn from the Sun to the planet, that is radius vector, sweeps equal areas in equal intervals of time. This law is also called as laws of areas. Next we go for third law of Kepler. According to Kepler's third law, the cube of the average distance of the planet from the sun varies as the square of the period of its revolution. That is t square proportional to d cube. Already we know that the length of the line drawn from sun to planet is not constant. It is not same in an elliptical orbit. Therefore, the distance between planet and sun is taken as mean or average distance of these two positions. If t is the time period of revolution of the planet and d is the average distance of the planet from the sun, then Kepler's third law is t square proportional to d cube. If t1 and t2 are period of revolutions of two planets, d1 and d2 are the mean distances of the planets from the sun, then according to Kepler's third law, t1 square by t2 square, this is equal to d1 cube by d2 cube. This law is also called as a law of time periods. And now we discuss some principles related to orbiting of a satellite. Already we know that when an object is dropped, it reaches the earth along the vertical line in the absence of air resistance. Similarly, if the object is thrown horizontally with some initial velocity, it takes a curved path, but still it reaches the earth. Now from this height, we go on increase the initial velocity. Then what happens? The range will increase. Thus, the initial velocity increases, greater is the radius of the curved path. If the object is given an initial horizontal velocity such that the radius of this curved path is equal to or greater than the radius of the earth, then what happens? Now this is the curved path. Can it return to earth? No, it will not return to earth. For this path it can reach, for this path it can reach, for this range it can reach. If the range is more than the radius of the earth, then this object cannot return to earth. Now this object becomes an artificial satellite. It orbits around the earth and the object becomes an artificial satellite. This is the principle we use in launching the satellite. When this object is moving around a planet, for what velocity the object will orbit around the earth. In general, satellites are taken to required height and are given a required horizontal velocity such that it revolves around the planet. This horizontal velocity with which the satellite revolves around the planet is called orbital velocity. Now we are going to derive an expression for an orbital velocity. Suppose we consider a satellite moving around a planet. When it is moving around a planet in a circular path, do you know which kind of forces are acting on it? Yes, one is the force towards the center of the earth. This is centripetal force, and this is the force required for the satellite to move around the earth. The centripetal force required for the satellite provided by gravitational force of attraction between the satellite and planet. And due to the motion of this object along the circular path, and another force is acting, which is pseudo force, which is called centrifugal force. The orbit is stationary means centripetal and centrifugal forces acting on the object are same. Now in this case, the centripetal force, this is equal to gravitational force between satellite and planet. If we consider the object is moving with velocity v0, this v0 is orbital velocity, then centripetal force is mv0 square by r. This is equal to gravitational force between satellite and planet, which is g/mm by r square. Here small m is the mass of the satellite, v0 is the orbital velocity, capital M is the mass of the planet, r is the distance of the object or satellite from the center of the earth, capital G is universal gravitational constant. From this we can write v0 square equal to gm by r. But what is r? If capital R is the radius of the planet, h is the height of the satellite from the surface, then we can write small r equal to r plus h. Therefore, v0 equal to root of gm by r plus h. If h is very less compared to capital R, that is, if the height is very less compared to the radius of the planet, then this can be written as V naught equal to root of gm by r. Already we know that the acceleration due to gravity on a planet small g equal to gm by r square. Therefore, V naught equal to root of g into r. This is the orbital velocity. Now, one thing we have to observe. The orbital velocity is independent of mass of the object. If the planet is Earth, the orbital velocity for a satellite which is moving nearer to Earth's surface is 7.9 km per second. This we get by substituting the value of small g 9.8 meter per second square and capital R, that is the radius of Earth, 6400 kilometers. Escape velocity. We know that when an object is thrown up, what happens? Again it returns to Earth. If you throw with larger velocity, again it returns to Earth, but it reaches more height compared to previous one. I want to throw this object so that it never return to Earth again. Then what may be the condition? For this you think, why this object is not able to escape from the Earth's surface? Yes, some energy binds this object towards the Earth. Or we can say, at this position, because of some potential energy, this object is having some potential energy. Due to that, it bound to Earth. If you throw with more energy, more than this potential energy, then it can escape from it. You are throwing means you are giving some kinetic energy. If this kinetic energy is more than the potential energy with which it is attached to the Earth, then what happens? Yes, it can escape. That means if you throw this object with some velocity so that the kinetic energy can overcome potential energy, then the object can escape from Earth's surface. And that velocity is called escape velocity. That is, escape velocity is the minimum velocity required for a satellite or for any object to escape from Earth's surface from the gravitational pull. In this case, to escape from Earth's gravitational pull, work has to be done against gravitational force, and the work done appears as kinetic energy of the satellite. That means the kinetic energy of this object should equal to work done against the gravitational force, or the magnitude of potential energy with which it is bound to Earth. Here we can write half mv square. If ve is the velocity required, that is escape velocity, the kinetic energy is half mve square. This is equal to g capital M small m by r. This is the gravitational potential energy or work done against gravitational force. Work done against gravitational force is nothing but gmm by r square into r. This is equal to gmm by r. Now from this we can write ve equal to root of 2gm by capital R. Already we know that the acceleration due to gravity small g equal to gm by r square. Therefore, ve equal to root of 2 into g into capital R, where small g is the acceleration due to gravity, r is the radius of the planet. In case of Earth, small g is 9.8 meter per second square and the radius is 6400 kilometers. Therefore, the escape velocity is 11.2 kilometer per second. That means if you can throw an object with a velocity 11.2 kilometer per second, it never returned to Earth. This velocity, the minimum velocity to escape from Earth's gravitational pull, is called escape velocity. What is the relation between orbital velocity and escape velocity? Orbital velocity is v naught equal to root gr. Escape velocity is v equal to root of 2gr. From these two equations we can write the escape velocity v equal to root 2 into v naught, or v naught equal to 1 by root 2 into ve. This is the relation between escape velocity and orbital velocity. We take some problems related to Kepler's law. You say this example. The time taken by Mars is 1.88 years to go round the Sun. Find the ratio of average distance between the Mars and Sun to that between Earth and the Sun. What is given in our problem is Mars takes 1.88 years to go round the Sun. How much time Earth takes? Yes, it is 1 year. We are asked to find what is the ratio of distances between Sun to Mars and Sun to Earth. Already we know that t square proportional to d cube according to Kepler's third law, where t is the time period of revolution of the planet, d is the average distance between sun and planet. From Kepler's third law, we can write t1 square by t2 square equal to d1 cube by d2 cube. Here t1 and t2 are the time periods of Mars and Earth respectively. t1 is 1.88 years and t2 is 1 year. Therefore, t1 square by t2 square is 1.88 whole square by 1 square. This is equal to d1 cube by d2 cube. From this we can write d1 by d2 whole cube equal to 3.534 by 1 and d1 by d2 is 1.52. The ratio of average distances between Mars and Sun and Earth and Sun is 1.52. Now we take another problem. What is the acceleration due to gravity on the top of Mount Everest, whose height is 8,848 meters, if the acceleration due to gravity on the surface of Earth is 9.8 meter per second square and the radius of Earth is 6,400 kilometers. Already we know that the acceleration due to gravity at some height, this is given by g prime equal to g divided by 1 plus h by r whole square, where g prime is the acceleration due to gravity at that height, g is acceleration due to gravity on the surface of the Earth, h is the height and r is the radius of the Earth. Now in this case, we are asked to find what is the acceleration due to gravity at a height 8,848 meters. If we compare the value of h with the radius of the Earth, the value of h is 8,848 meter, that is 8.848 kilometer, and the radius of Earth is 6,400 kilometer. Since h is very small compared to r, 1 plus h square by r square to the power of minus 1 by 2 can be written as 1 minus 2h by r using binomial theorem, neglecting the higher powers. Therefore, the acceleration due to gravity at height h, g prime is g into 1 minus 2h by r, and this is valid when h is small. Now substituting the values of h, r and g. In our problem it is given g is 9.8 meter per second square, h is 8,848 meter or 8.848 kilometer, r is 6,400 kilometer. Now g prime equal to 9.8 into 1 minus 2 into 8.848 into 10 power 3 divided by 6,400 into 10 power 3. Converting kilometer into meter, 1 kilometer is 10 power 3 meters. Now from this g prime equal to 9.8 into 1 minus 0.0028, this is equal to 9.8 into 0.9972. We get g prime equal to 9.77 meter per second square. This is the value of acceleration due to gravity on Mount Everest. We go for another problem. A satellite is to revolve around the Earth in an orbit of 8,000 km. With what speed should the satellite be projected into the orbit? What will be its time period? In this problem, we are asked to find what is the speed of the satellite to move around the Earth at a height 8,000 km. And also we have to find the time period of the satellite. For a satellite to move around the Earth, to maintain a constant orbit, the velocity required is nothing but the orbital velocity, and it is given by root of gm by r plus h. This also can be written as root of gr square by r plus h, where capital R is the radius of the Earth, h is height of the satellite from the surface of the Earth, and small g is the acceleration due to gravity, and capital G is universal gravitational constant. In this case, the radius of the orbit of the satellite is small r plus h, that is 6,400 km plus 8,000 km. Here capital R is the radius of the Earth, that is 6,400 km, and small h is the height of the satellite from the surface of the Earth. This is 14,400 km. On substituting the values, we get the orbital velocity v0 equal to square root of 6.4 into 10 power 6 whole square into 9.8 by 14.4 into 10 power 6. On simplification, we get this is equal to 6.4 into 10 power 6 into root of 0.68 into 10 power minus 6. This is equal to 6.4 into 10 power 3 into 0.825. Now this is equal to 5.28 into 10 power 3 meters per second or 5.28 kilometers per second. The time period of the satellite is t equal to 2 pi r by v naught. 2 into pi into r is the distance of the satellite from the center of the earth. It is 14,400 into 10 power 3 divided by the orbital velocity is 5,280 meters per second. On simplification, we get this is equal to 17,127.3 seconds. In minutes, to convert into minutes, just to divide with 60. Now this is equal to 285.5 minutes. The same answer in hours is 4.76 hours.